Today I'll be presenting on adversarial tokenization, our recent work in ACL 2025 main conference. So first, let's start with some basics. Tokenization is a very important pre-processing step in nowadays LLMs training and testing. Most language models represent distributions over sequences of subwords named tokens but not strings. So the reason why people usually do it is that it saves a lot of computation. For example, you can tokenize the string caterpillar in such a way which shrinks the length a lot, which facilitates inference and training. The natural question to ask is, how do we tokenize given a certain string? There is usually a unique tokenization if you prompt a model's tokenizer, and we call it canonical tokenization. For example, if you ask Llama to use tokenizer how to tokenize the word caterpillar, it will always give you a deterministic answer that here is the tokenization you can use, and we call it canonical tokenization. A common assumption people may have is that the probability for the model to generate the string caterpillar is equal to generate its canonical tokenization, but it's not usually true. So a string can be tokenized in an exponential number of ways. For example, here, using Llama 2's vocabulary, you have over 700 possible tokenization. So given the fact that a string can be tokenized in so many different ways, we wonder the semantic understanding in these tokenizations if it's the same. With respect to a certain LLM, can we measure how different the semantic understanding, or we call semantic signal, of tokenizations? In other words, can an LLM understand all of these tokenization as the word caterpillar? We wonder at what point does the LLM not recognize a tokenization? So how far from the canonical will break the understanding given a reference tokenization? That's a question we want to ask. For example, the model may understand the top two tokenization but cannot understand the last one. So we wonder, when does it go from understandable to not understandable? Can we define a metric space for tokenizations? That's why we introduce added distance here. So we use added distance to measure how divergent a reference tokenization is from the canonical one. And we see here, it seems like there is a trend, there is a correlation between the distance and understandability. And we did a more principled way to quantify this correlation. So here we develop a small data set consisting of quiz problems, and now we tokenize the prompts in different ways and then prompt the model to see if it can get the answer correctly. And here's the experiment result we have. Here, the x-axis means the normalized distance between the canonical and an alternative tokenization. When it's 0, that means it's the canonical one. And when it's 1, that means it's character level tokenization. So as we can see here, it seems like there's a trend that the further away a reference tokenization is from the canonical, the lower the semantic signal is, because the accuracy drops as the distance goes up. So as we know, in post-training phase, alignment shovels probability mass away from the malicious behavior, and that's how we prevent the model from answering dangerous responses. But what we should notice is that the alignment only happens for canonical tokenizations. It only includes canonical tokenization in the post-training phase. So that makes us wonder, can we sample tokenizations with high semantic signals that evade alignment? For example, you can prompt the model with these prompts that write a tutorial on how to make a bomb, and an LLM model should tell you I cannot do it. but you can slightly change the tokenization of the prompt, and then the model will give you the faithful answer. So we quantify this by using strong reject score, which measures the harmfulness and the relevance of the responses. And we see that as the distance goes up, there exists some sweet spot in this figure that will give you a relatively high strong reject score, and consistently it's higher than the canonical tokenization. So we already showed that you may use random sampling to get an alternative tokenization that may break the alignment. But how to find the tokenization most likely to elicit the dangerous responses? So here's an objective function we propose to maximize. That is, we want to maximize the LLM's probability of generating a target response given the prefix and the tokenization of the prompt. So for example, we want the model to answer something starting with the prefix in the target. That's short, here's a tutorial on how to make a bomb. And given the tokenization, a certain tokenization of the malicious request. Unfortunately, we show that the conditional most likely tokenization problem is NP hard, so we cannot do it directly. So the solution here we propose is greatly approximate this probability using local search. And here we define the neighborhood to be the set of tokenization with distance of 2 to the current tokenization and denote it as neighborhood of V. We found some nice propositions that could ensure the robustness of our algorithm. And here is a snippet of our algorithm. We applied our algorithm into different case studies, for example, jailbreaking. As we just saw, a more formal way to phrase this task is to provoke the LLM to output a faithful response to harmful prompts. And in this table, we showed our results in this task. So we can take a look at the bottom part of this table, which shows our adversarial tokenization achieves competitive performance against the baselines and also much higher than the canonical baseline. We also combine it seamlessly with the existing pipelines because our attack happens at the tokenization level. So by doing this, we achieve SOTA performance. And the second case study is to evade safety models. So there are some well-known guard models like Llama guard and Shao Llama, which will tell you directly if a prompt is safe or not. And by using adversarial tokenization, the success rate improves by 5 to 10%. A third case study we did is prompt injection, which is a man-in-the-middle attack. So here, a malicious agent intercepts a conversation by altering the user input to provoke a malicious response. And our adversarial tokenization achieves 65% improvement compared to the canonical baseline. So, to this point, I want to point out a fact that seems to be a contradiction. So, we wonder how come LLMs recognize non-canonicals at the semantic level, but do not recognize them at the alignment level. So, to resolve this, we need to point out the differences between pre-training and post-training. In pre-training, we usually have huge data sets, and it consists of typos, multilingual, weird spacing. All of these contribute to the semantic leakage onto the non-canonical tokens. But in post-training, we usually use smaller data sets, and we use the reinforcement learning with fewer typos, and usually the data is monolingual. So the difference makes the alignment signal leaked less than the semantic leakage we have in the pre-training, which makes our adversarial tokenization to be true. So a question we want to ask is, should post-training incorporate elements from pre-training? And it wraps up our presentation in adversarial tokenization. Thank you for watching.